Hi guys, this is Gunjan and I'm with my teammates Shivansh and Dipesh and we'll be discussing about deadlock avoidance algorithm today. So imagine this, 5 co-workers are sharing 3 printers and 2 scanners. Each person needs both and suddenly nothing moves. No one can finish. That's a deadlock. Now imagine if we could plan things so this freeze never happens. That's what avoidance algorithm does. Let's dive in better. So, a deadlock happens when processes are stuck waiting for each other's resources indefinitely, like cars blocking each other at four-way stop. The four conditions that make deadlock possible are mutual exclusion. One, only one process can use a resource at a time. Hold and wait, a process holds one resource and waits for another. No preemption, you can't forcibly take away a resource. And circular wait, a chain where each process waits for the next. If all four happen together, we've got a deadlock. So, before jumping ahead, let's make one thing clear. Deadlock prevention stops at least one of those four conditions from ever happening. Deadlock detection lets it happen and then tries to fix it. And then there is deadlock avoidance, our focus, which allows flexible resource allocation but checks first if it keeps the system safe. Think of it like crossing the road. Prevention puts up the barricades, detection lets you cross and then fixes the chaos later, like the police. Avoidance check both sides before stepping. Alright, so for systems where there's only one instance of each resource, we can visualize requests and allocations with a resource allocation graph. If a cycle appears, that's a warning of possible deadlock. But for systems with multiple instances of resources, this simple graph isn't enough, and that's where the banker's algorithm come in. The banker's algorithm was proposed by Edsger in 1965. It is based on a banking analogy. A banker won't grant a loan unless they're sure they can fulfill all commitments safely, even if everyone asks for the maximum at once. Similarly, the operating system checks if granting a request keeps the system safe. Go ahead. If not, the process will wait.
Let's see what it tracks. Available of m, that is number of free resources of each type, max of n of m, that is maximum demand for each process, allocation of n of m, that is currently allocated, need of n of m, that is max minus allocation. When a process pi makes a request, the system checks request of I less than equals to need of I, and also it checks request of I less than equals to available. If both are true, it temporarily allocates the resources and runs the safety algorithm to see if the system is still safe. To check if a system is safe, start with work equals to available and finish I equals to false for all I. Find a process where need of I less than equals to work, pretend it finishes, add its allocation to work, mark finish I equals to true. Repeat until all processes finish. If all finish of I equals to true, you are in a safe state. If not, it's unsafe, meaning deadlock could occur. Let's see a simple example. In this, if the system finds a sequence like P2, P1, P3 that's a safe sequence, it means every process can finish one by one without deadlock. If no such sequence exists, the system marks it as unsafe. Now for in C, for I equals to 0, I less than n, I plus plus, finish of I equals to false, work is equals to available. While exists I, where finish I equal false and need of I less than equals to work, work equals to work plus allocation of I, finish of I equals to true. If all finish of I, print f safe state, else printf unsafe state.
This is the essential banker's algorithm. It only grants requests that keep the system safe. Now coming to edge cases and complexity point. If a process requests more than its declared maximum, it's an error. If the system is already unsafe, the process must wait until it becomes safe again. The algorithm checks each process repeatedly, making its complexity roughly so it's reliable but not the fastest for large system. Now just take a real world relevance. In reality, Modern operating systems rarely use the banker's algorithm directly because processes don't declare the maximum needs in advance. However, its logic forms the foundation for many resource management policies in databases, in embedded systems, and even in cloud schedulers. So while it's theoretical, it's a concept every computer scientist must understand. Now just take some of the advantages. It prevents deadlock completely. It ensures predictable resource use. It helps in designing safer scheduling system. Now coming to disadvantages, it needs advanced knowledge of maximum resource needs. It's computationally heavy for large system. It is not practical in dynamic environment. Now let's wrap it up with a short summary. So deadlock avoidance, especially the banker's algorithm, is all about staying safe before it's too late. It's like a smart banker or a cautious driver, always checking before saying yes. Thank you.